Imagine if the Earth's core, the very heart of our planet, could be transformed into a molten inferno, all because of a mysterious entity known as dark matter. This isn't just a sci-fi plot twist. It's a real possibility that has scientists intrigued and concerned. The dark matter dilemma. Scientists have long been on a quest to understand the nature of dark matter, a substance that makes up most of the universe's mass yet remains elusive. In this pursuit, they've discovered that sometimes what dark matter doesn't do is just as revealing as what it does. For instance, the absence of a specific phenomenon can narrow down the possibilities of what dark matter could be. A dark inferno in the making. Here's where it gets fascinating. A recent study suggests that certain models and particle masses of dark matter, if correct, could lead to a dark inferno within the Earth's core. This inferno would be the result of dark matter particles and antiparticles annihilating each other, releasing energy in the form of heat. The key phrase here is within detectable limits. If this heat is not significant enough, it might go unnoticed. But wait, isn't this a bit like a Hollywood movie? Well, not quite. While the idea of a team of scientists saving the Earth from a molten core is thrilling, the reality is more nuanced. Dr. Christopher Cappiello and Dr. Tansu Daylan propose that dark matter particles are indeed accumulating in the Earth's core, potentially generating heat. The consensus among physicists is that dark matter is crucial to explaining galaxy movements and light bending. The challenge lies in identifying its composition, with various models and particle masses on the table. These models agree that dark matter congregates where gravity is strongest, including the center of galaxies and stars, and to a lesser degree the Earth's core. The core's fate, according to Cappiello and Daylan. Many models predict that dark matter particles and antiparticles would meet and annihilate at the Earth's core. This annihilation process would generate energy, which would likely manifest as heat. They emphasize that the annihilation rate is directly proportional to the square of the dark matter density. While this concept isn't entirely new, the researchers focus on the heat's impact once it reaches the surface. They argue that unless the energy release is substantial, it might be challenging to differentiate it from heat produced by radioactive decay. The dark inferno scenario. Cappiello and Daylan introduce the term dark inferno to describe a scenario where the heat generated is sufficient to melt part of the Earth's core. This idea is not just theoretical. Seismic data confirms the existence of a solid core approximately 2,500 kilometers wide. The researchers suggest that a small enough molten area could have formed without detection. Through their analysis, they estimate that this liquid core could have a maximum radius of 400 kilometers. Consequently, they believe this sets an upper limit on the energy release at around 20 terawatts. The Earth's core is indeed hot, but this heat is generally attributed to the radioactive decay of isotopes like uranium and thorium. The heat from matter-antimatter annihilation would be a more efficient process. However, determining the energy release isn't straightforward. It's not just about gravity pulling dark matter into the core. Some energy loss is required during collisions between dark matter and ordinary matter particles, causing orbital decay. The mass of dark matter particles plays a crucial role in how they concentrate in the core. The particle mass conundrum. For lighter particles, existing studies have already established lower limits on energy release, making Cappiello and Daylan's work less groundbreaking. However, for heavier particles, their research offers new insights into what could occur without detection. It's essential to remember that these findings rely on specific assumptions about dark matter's characteristics. For instance, if dark antimatter is scarce, like ordinary antimatter, annihilation rates would be low. Additionally, if the energy release is primarily in the form of neutrinos, the heating effect would be minimal and challenging to observe. This research invites further exploration and discussion, leaving us with a captivating yet controversial glimpse into the potential effects of dark matter on our planet.